everyone! Cody here, and welcome back to my laboratory. So it seems like about this time of year, early February, I always get this strange urge to extract precious metals from something. So let's do another precious metals recovery video, shall we? Let's do it on another one of my interests, and that is space rocks. We're going to be doing some asteroid mining. Unfortunately, I am still stuck here on the Earth. You know, this gravity well is pretty hard to get away from. So, space rocks, I'm not going to be able to go to them. Fortunately, they do occasionally come to us in the form of meteorites. This is one that I've personally found that has landed out in the desert, and here's one that I purchased on eBay. These are the most common types of meteorites, the chondrites, the material that condensed from the solar nebula as the solar system was forming. These are the oldest rocks that you can reasonably have. I think that's so cool. And they do contain precious metals. In fact, they contain all of the elements. It's just a mix of everything that was in the solar nebula at the time, essentially. You know, except for the helium and hydrogen stuff that boils out. Now you might be thinking, well, didn't the Earth form from the same material? And that is true. The bulk composition of the Earth is the same as this rock. The difference is when the Earth formed, material slammed into it very hard. It was accreting material falling down that gravitational well. All that energy got turned into heat, so the Earth was completely melted when it formed. And all of the heavier materials that were in their elemental state in those conditions, so iron and siderophile, or iron-loving elements, in the middle of the periodic table, sank down to the Earth's core. So the Earth contains lots of gold and platinum and stuff too. It's just 4,000 miles down, and 4,000 miles of rock, which is superheated under extreme pressure. It's honestly easier to get it out of space. But regardless of method, I have acquired a sample of asteroid material. So, what is the first step for extracting the precious metals? Well, may as well do the same thing that the Earth did and melt it into a liquid and let it separate by density. Have the heavier iron fall through the material, picking up the precious metals and collecting it down at the bottom of the crucible where it can be siphoned off. You'd probably want to have it like on a rotating arm or something, so your furnace has some artificial gravity, but that's all relatively trivial. And definitely worth it because you would be concentrating it by perhaps as much as a factor of 20 or more, depending on the starting material. So that would be a good first step. Fortunately, I don't actually have to do that. I don't have to destroy this meteorite any more than I already have, because that process is also natural out in space, and smaller planetoids that were formed in the early solar system did melt completely and did have enough gravity to have the material separate out. But those smaller planetoids were small enough they were to cool off completely and then were shattered by another impact. So you actually have bits of material which is already concentrated flying around out in space, and occasionally one does hit the Earth. Here's one example. This is some fragments of the Campo del Cielo iron meteorite, which landed over Argentina. Hopefully I pronounced that right. But this is some concentrated ore, which just fell to the Earth. Again.
Now, iron meteorite like this is much less common than the ordinary chondrites. The material that hits the Earth is mostly this. But iron meteorites are overrepresented in the samples of meteorites that humans have because, well, they last a bit longer on the surface of the Earth, they're a little bit more durable, and they're more obviously not from around here. This just looks like any other rock, whereas you find something that looks like this, it's like, oh, that is weird.
Now the process I will use is probably going to be different than what you'll actually use out in space.
One attractive possibility is the Mond Carbonyl process, which uses high-pressure carbon monoxide to complex the iron and nickel into a volatile form, such that the elements can be separated through simple distillation. And then, with just mild heating, the carbonyls can be decomposed back into the metal and carbon monoxide again. So, once everything's started, the only inputs are the raw ore and heat. I don't have extremely high-pressure silver-lined reaction vessels, and carbon monoxide makes me a little bit nervous, so I'm going to use just whatever is most convenient, probably just strong acids, processes I've done before. But let's go weigh out a sample and see how much precious metals we can get out of it. Dump this out on a scale. Okay, I have just over 200 grams of meteorite. That'll make a pretty good sample. Now, the first thing we need to do to this, to get the precious metals out, is to make the pieces a little bit smaller. So how am I going to make this meteorite into smaller pieces? You see, a meteorite, it's a ductile metal. It's malleable. So if I hit it with a hammer, it doesn't break. It just bends. In this case, I've dented it a little bit. However, if I cool it down with some liquid nitrogen, you see right there, pull this piece out. Now when I hit it, it loses its ductility, and I'm able to shatter it. See that? And now it's in smaller pieces. Out in space, this cooling could be accomplished just by putting the asteroid material in the shade and letting it radiate its heat out into space, similar to what we do with the James Webb Space Telescope. Now that I have successfully increased the surface area of the meteorite somewhat, it will make the next step go much faster. And that is to dissolve the bulk of the metal, the iron, nickel, cobalt, using some hydrochloric acid. So I'll just dump in here. I'm using a crock pot just to keep things warm, because I'm doing this outside during the winter. Lid on, turn it to low. And as you can see, the meteorite has already begun reacting with the acid. This is forming ferrous chloride, which is green, and a little bit of ferric chloride, which is orange, probably due to some oxide impurities on the meteorite, and some hydrogen gas, which you can see bubbling up. And actually, I can also smell a little bit of rotten eggs coming off of this, because the meteorite also contains iron and nickel sulfide, which is reacting with the acid to form hydrogen sulfide gas. Which is one reason why I'm doing this outside next to a fan, so I can have plenty of ventilation so those toxic gases don't build up. It's starting to really react now. But what I'm doing here isn't actually a whole lot different than the Mond process. I'm just using hydrogen chloride instead of carbon monoxide. But the net effect is still the same. I'm getting rid of the base metals, dissolving them away, and leaving the precious metals behind. The precious metals, the platinum, the iridium and stuff, those are unable to be oxidized to a soluble form by the acid. Likewise, they'd be unable to be dissolved by the carbon monoxide in the Mond process. Okay, it's been several hours. And the acid is mostly spent at this point. Still reacting a little, as you can see here. Still some bits of meteorite. The main problem is that the ferrous chloride has reached its solubility limit, so I need to replace the fluid here. I'm going to pour what I've got off into this cylinder. So, Now I'm going to add some more acid. Okay, see how things are doing. Alright, looks like all the meteorite has been dissolved. Yep, it's pretty good. Okay, there's my dissolved meteorite. Looks like some ferrous chloride has crystallized out. Ferric chloride is being formed as the ferrous chloride is oxidized by the air. So I'm going to add some distilled water in order to dissolve that ferrous chloride. Put a bunch in, give it a stir. And now, in theory, my precious metals should eventually settle out of the solution and form a powder on the bottom of this glass cylinder here. Now you might be able to see some sparkly bits, some space glitter here. At first I thought, well, hey, maybe this glitteriness is what I'm looking for. The platinum group metals are, of course, known for their shininess, but there's a few problems with that. First, when you dissolve a base metal that contains the noble metals, usually you end up with a brownish black powder, like what I've got here, because the particles end up being so small that they don't reflect light the same way that a larger piece of metal does. But hey, maybe the meteoritic material cooled over such a long period of time that the crystals were able to grow to a larger size. You know, you see that when you etch a meteorite. The crystals of the iron are quite large. But then if this is the platinum group metals as large crystals, wouldn't they be heavy and sink out of solution almost immediately? You know, the platinum group metals, they're some of the densest elements. So that can't be it. These are probably not the precious metal. So I still was wondering what this was, so I did some research, and apparently moissanite, natural silicon carbide, was first discovered by dissolving an iron meteorite. So hey, maybe this is silicon carbide. That's pretty cool. That's a mineral you don't really find on the Earth. But then I brought a magnet next to it, and you can see the particles are obviously attracted to the magnet. That looks pretty interesting, doesn't it? Oh, that's really cool. So moissanite silicon carbide is not magnetic, but this is clearly very magnetic. So now I'm leaning towards it being perhaps nickel disulfide or something that is not soluble in hydrochloric acid but is still magnetic. I'm still not entirely sure, so if anyone has some ideas, I'd love to hear it. For now, let's just let it all settle out and then separate it from the solution. In case anyone's wondering about the decanted solution, my plan is to use it as an iron source for growing algae and other crops. But first I need to remove the nickel. You see, nickel is toxic in large amounts, and the 5% that was in the original meteorite is enough to be a problem. So to remove it, I first need to oxidize the solution. So for that, I'm just going to use a little bit of hydrogen peroxide, which should form the ferric chloride, which is orange. There was already a bunch of it formed already just from atmospheric oxygen oxidizing it. This is just a little bit faster. Now that this is thoroughly oxidized, I'm going to add some ammonium hydroxide, which will precipitate the iron as iron 3 hydroxide, which is essentially rust, while also complexing the nickel and also the cobalt as a hexyamine complex, which will remain in solution. So all I need to do is filter it out. So now I've got the iron hydroxide, which I could use as is or convert to iron chelate, and of course the nickel and cobalt, which I'll find something to do with it. Okay, back to the main extraction. Most of the liquid has been siphoned out. As you can see, there's still a little bit left. It's still very green. Lots of ferrous chloride still left. I'll just rinse with a little bit more distilled water and let it settle out again. Got it rinsed into a smaller beaker. Oh, there we are. We've moved most of the chloride solution. I'm actually going to grab a sample here. Let's go put this under a microscope and see how it looks. So here we are. The majority of the particles still just look shiny and metallic. Doesn't really tell us much. But I do see some green particles there. That looks like olivine. That's pretty cool. So I evaporated off the water. Now let's dig this material from the bottom of the beaker and transfer it into a little crucible. So time to load it into the furnace. Notice I'm not using any kind of flux. The idea here is that if that is a sulfide mineral, roasting it in air should destroy it. The precious metals, the platinum, iridium, palladium, those should be unaffected. I will lose the osmium and ruthenium though. Those form volatile oxides. Yeah, it's cooking. Once it's done roasting, however, I will need some flux. So I'm going to make some flux using some sand, sodium carbonate, a pinch of borax, and some lead powder. This is silver free. Now this will dissolve the oxides as well as the silicates and carbides, and the lead will melt and collect the precious metals into an alloy, just like the iron did originally. Should be roasted. So now let's put in the flux. I'm going to do it about half at a time, just so I don't cause it to boil over. Okay. See, looks like it's done. Pull it out. There. I'll just let it cool. It's cooled off. Now bust it open. There's the lead. Very nice. Just clean that off a little bit. Voila! He's clean. So now I'm going to put it back in the furnace in the little cupel dish, which is made out of bone ash. As the lead oxidizes, the lead oxide will be absorbed by the dish, and the platinum group metals should be left behind. Let's see how it's doing. It's almost done. Just like that, installation is finished. Let's pull it out of there. See how it looks. Nice and toasty. Now you gotta beat a metal. Nice. So it's cooled off, and there's our valuable metals. As they say, if you cupel it, you can sell it. But how much do I have here? Spoilers, not much. I'll pull it off of the cupel and put it on the scale, but I can already tell you it's not going to measure probably anything on the scale. I got a hold of it. Let's go set it on the scale. There we are. Hey, it did read something. It might have been the wind currents from my hand. Based on my experience, I'd say this is between 1/2 and 1 milligram worth of metal. If we have a look at it under the microscope, you can see here that it's actually a spongy mass. The furnace wasn't able to get hot enough to actually melt the platinum group metals, so what I have here is essentially a fine powder that's glued together with the lead oxide. A quick test to confirm that I do have platinum group elements. They are good catalysts, so they should decompose hydrogen peroxide on contact. So let's add the peroxide. There we go. Got some effervescence as it catalyzes the peroxide into oxygen and water.
So there you have it. I've managed to acquire a few cents worth of platinum group metals, and all it took was $200 in meteorite, $100 in chemicals and supplies, and a little over 2 weeks of work. Bargain! But of course, the whole point of this wasn't to actually make money off the extraction. It was to show that the precious metals are there and to give you sort of a taste of a future massive industry. You see, that amount of value extracted from half a pound of rock would be considered a very valuable ore here on the Earth. There are mines that are processing hundreds of tons of rock per minute with much less values than that. And that's not even including the fact that the nickel and the iron are quite valuable. And other people have done analyses on meteorites using much more sophisticated equipment than I have, and that indicates that I had a yield of maybe only 10 to 20%. So yes, there's platinum in them there asteroids, and also gold and iron and phosphorus and sulfur, water, all sorts of valuable stuff. So asteroid mining is something that's definitely going to happen in the future. However, hopefully I've impressed upon you just how much of a challenge it's actually going to be. You're not going to be sending a plucky space probe to an asteroid and picking up platinum blocks, for instance. It's not going to be that trivial. There's going to be an industrial plant built out in space, and I can't wait to see it. And hey, maybe one day I'll be part of it. Perhaps I'll make a bunch of synthetic meteorite to work with so I'm not destroying like actual valuable specimens. And if I play around with it enough, perhaps I'll come up with a process that actually gets used one day. That'd be pretty cool, right? But until then, if you guys want more, I will be on the Event Horizon podcast with John Michael Gautier. We talk about this and other things that I do on my channel. I'll leave a link down in the description for you to check it out. But anyway, I'll see you next time.